Welcome to The Explainer. Today, we're looking at something most of us drive over every single day without giving it a second thought. But I promise you, by the end of this, you'll never look at a freshly paved road the same way again. Because building a road that actually lasts, it isn't just about driving massive, heavy machinery over hot asphalt or dirt. It requires highly engineered physical science. We're talking about a delicate, calculated dance of macroscopic forces, centrifugal energy, and microscopic particle movement. Yep, today we're getting into the absolute physics of vibratory rollers.
Okay, let's dive into this. Is simply being heavy actually enough to build a road? It's a completely natural assumption, right? Just put a massive, heavy piece of metal on top of loose dirt, let gravity do its thing, and boom, you have a solid foundation. But here's the reality check. Roads face incredibly brutal, repeated external forces. We are talking about the relentless kinetic pounding of heavy traffic loads, massive thermodynamic shifts from temperature changes, the penetrating damage of heavy rainfall, and, depending on where you live, even the earth-shaking stress of localized earthquakes. If a road is just kind of pressed down by brute force, it just won't survive. We need something much more scientifically rigorous.
Looking right here at the slide, you can see what's happening on a microscopic level. Soil and crushed stone are full of these hidden dangers known as voids. There's actually a massive amount of empty space sitting right between the solid matter in these particle structures. And these voids, they're filled with water and air. If those air pockets are too large, the solid particles literally have room to move around and deform easily whenever a heavy truck drives over them. And it gets worse. When rainwater penetrates the material, it acts exactly like a lubricant inside those voids, which severely reduces the structural friction between particles. Essentially, those empty spaces drastically undermine the bearing strength of the entire road base.
So the crucial point is getting rid of those voids. That is the essential problem we have to solve here, and it's the exact physical definition of compaction, mechanically reducing the air and water from the material. We're taking that naturally loose arrangement and forcing it into a tight, incredibly dense cluster. By eliminating the empty space, the particles are forced to physically touch. This drastic increase in surface contact mathematically multiplies the friction between them. And that amplified friction, that is what ultimately gives the ground its incredible bearing force and shear density, completely transforming loose dirt into a load-bearing foundation. Now, achieving that mechanical reduction requires a really precise application of force. Throughout history and even in modern engineering, we rely on four primary methods of compaction: gravity, kneading, vibration, and impact. Ancient builders relied almost entirely on static gravity to compact their rudimentary roads. But modern physics has taught us that to build incredibly durable highways capable of supporting millions of vehicles a year, we need a highly sophisticated, precisely calibrated mix of all four of these mechanical actions. Let's compare the first two mechanisms for a second. Gravity versus kneading. Gravity compaction is basically what you get from a classic smooth steel roller. It's simply a heavy weight pushing straight down into the earth. But kneading? Kneading is a much more fascinating physical process. Think about making bread or pasta dough. When you knead dough, you aren't just pressing flatly down, you are actively pushing the material in all directions to work the microscopic pockets of air out of it. Pneumatic tire rollers do the exact same thing to roads. The flexible rubber tires use a kneading action, shifting the hot asphalt multidirectionally to squeeze out voids way more effectively than just a flat static weight ever could. The third method is impact compaction. This one is pure, straightforward kinetic force. Machines like rammers take a heavy mass and literally drop it onto the ground from a calculated height. The physical impact sends a deep kinetic shockwave traveling down into the material, violently forcing the particles together. It's a highly effective method for smaller, targeted areas or deep utility trenches where you need rapid consolidation. But you know what? While gravity, kneading, and impact are all excellent tools, they're ultimately just the opening acts for the true scientific marvel of modern road construction. And that brings us to vibration. When we talk about vibration and compaction, we're talking about actively breaking the fundamental rules of microscopic friction. Instead of just pushing down from the top and hoping the weight transfers all the way to the bottom layers, vibration actually releases the intermeshing between the individual particles. By rapidly shaking them at very specific frequencies, the static friction, temporarily holding them in their loose state, is just completely broken. This momentary weightlessness allows the particles to freely compress under the mass of the machine. And this brilliantly illustrates what happens next. This application of physics forces those once loose, jagged particles to shake, spin, and neatly intermesh with one another. Because that restrictive friction lock is completely broken by the vibrational frequency, the particles naturally settle into the absolute tightest, most densely packed configuration possible. It is no longer just a matter of squishing dirt together. It's practically vibrating the raw material into a solid, structurally sound interlocking foundation. It's almost like magic, but it's pure science.
But you might be wondering, how on earth does a massive steel machine actually generate that kind of ground-shaking power? Well, inside that giant steel drum is an eccentric rotating shaft. Now, eccentric simply means there's a heavy mass physically offset from the shaft's centerline. As this internal shaft rotates at incredibly high speeds, that unevenly distributed weight generates a massive, continuous 360-degree centrifugal force. That raw, physical energy is transferred right through the steel drum and directly down into the ground beneath it.
Engineers, however, didn't stop at just creating raw centrifugal force. They actually figured out how to precisely steer and direct this energy based on the job at hand. So, we have three main types of directed vibration. First, standard vibration is circular, pushing energy out in a full 360 degrees. This is the powerful, everyday go-to method. Second, we have vertical vibration, which uses two synchronized eccentric shafts to focus all the kinetic energy strictly up and down. This is specifically designed for incredibly thick soil layers, sometimes up to 60 centimeters deep. And finally, we have oscillation. This is a totally ingenious method that uses two counterweights rotating in opposite directions to completely cancel out the vertical movement, creating a purely horizontal, side-to-side force.
As you can see, the choice between standard circular vibration and oscillation comes down entirely to the depth and delicacy of the material. Oscillation is perfectly calibrated for thin lifts, meaning pavement layers that are 5 centimeters or less. Because the force is strictly horizontal, it's gentle enough for delicate bridge decks or residential areas where you absolutely don't want to rattle nearby houses off their foundations. Conversely, standard circular vibration is designed to aggressively penetrate deeply into the ground, making it the ideal physical tool for thick asphalt layers that are more than 5 centimeters deep.
So, you might ask, why not just use standard vertical or circular vibration for everything? Well, because physics always demands a trade-off. Conventional circular vibration creates a really powerful moment of inertia. When you use it on thin, hot asphalt, it actually pushes a bow wave of material right in front of the drum, much like the bow of a boat pushing through water. This microscopic wave can cause tiny hairline cracks in the asphalt mat, permanently damage the base structure, and completely ruin the smoothness of the road. Oscillation, by keeping the force entirely horizontal, cancels this destructive bow wave effect out completely.
Now, what's really interesting about this slide is what happens when we combine these compaction technologies. The result is unprecedented structural density. If you use a traditional static tire roller on an asphalt layer, you typically achieve 92% density at the top and 95% at the bottom, creating an uneven bottom-up gradient. If you use a standard double drum vibratory roller, it creates the reverse, a top-down gradient with 95% at the top but only 92% at the bottom. But when engineers perfectly combine standard vibration with the dynamic kneading action of pneumatic tires, the physics align. You achieve a perfect, uniform 95% density from the very top of the surface straight down to the base. It is a true masterpiece of applied engineering.
Let's zoom out for a second and look at the macro impact of this perfectly uniform density. It doesn't just mean the road physically lasts longer. A uniformly dense, incredibly smooth surface drastically reduces road noise for surrounding neighborhoods. For everyday drivers like us, less rolling resistance on a perfectly flat road means significantly better fuel consumption over the life of the highway. And for the construction crews, a modern 9-ton vibratory pneumatic machine can achieve the exact same compaction as an old-school massive 25-ton static model. That saves a staggering amount of hauling costs, logistics, and fuel just getting the equipment to the job site.
Which brings us to the end of our explainer with a question to ponder. The next time you're cruising down a perfectly smooth stretch of highway, feeling your car glide effortlessly over the asphalt, ask yourself, was this road just pressed down by brute force, or was it carefully, scientifically vibrated into perfection? Because as we've explored today, understanding microscopic particle physics, harnessing centrifugal forces, and actively manipulating friction are the true, hidden builders of the modern world. Thank you for joining me for this explainer, and keep questioning the physics of the world around you.